All right, looking at worksheet B numbers 3 and 4 for chapter 3. So starting off with number 3. So students enrolled at university, and then they're going to define a few things for us here. So let A be the event. Student chooses architecture, and then we got E for engineering, and then N for neither. So they give us a few values. Venn diagram is a great way to lay out information like this. All right, so one thing to keep in mind is if neither was 28%, that means the remaining 72% are either A or E. So in the idea of a Venn diagram, and we'll use a formula for this in a minute. So if we have our group for A or E, then our universal set, since we're dealing with percents, our universal set has to be 1 or 100%. So if I have 28% that is neither, that means, again, the remaining 72% must be either A or E. So I have 72% within that, and we got a formula for that that says A or E must equal A plus B, or sorry, A plus E, minus A and E, which we don't know what A and E is, so we're using that formula to solve for it. So that's the way we're going to start that out. So if we do the math on that, then we are left with 15% representing A and E. So I'll just write that out. So A and E we now know is 15%. So if we start filling out the diagram with the information that we know, I should have made that a little bigger there in the center, but we know that A and E, let's see if I can fit this in, represents that 15% that we have right there. So if we just kind of subtract our way out, we know that all of A was represented by 29%. So if this entire circle has to be 29%, well, we've already accounted for 15%. So if we do a little subtraction, 29 minus 15 tells me that there is another 14% that is A only. So architecture only. So again, you have all the people that do architecture. Some of those people that do architecture also do engineering, and the other people just do architecture only. So that's kind of the way that the architecture group was broken up. So we can do the same thing with the engineering group. So they were 58%. So of the 58% that make up circle E, 15 of those 58 also do architecture. So the remaining 43, so we're just subtracting, do engineering only. But you can see that the total for engineering does make up 58% total, which is the information we're given right here. So now we kind of have all the information broken down and separated out. So for part A, it says by the use of a Venn diagram or otherwise. So they're kind of suggesting this is the best way to go, but if you want to use another method, that's okay too. You do want to show work for this stuff. There's definitely cases in IB testing where if you showed no work but still get the right answer, you don't earn all of the points. And so some of those points get dedicated to the work shown. So really important that you show work whenever possible to make sure you get all the points. But anyway, we answered the question already for part A. So that probability that a student chooses both. So we use the formula to do that. We've also represented it within our Venn diagram. So 15% that a student would choose both. So let's move on to part B. So calculate the probability that a student does architecture given that they do engineering. So we've seen before with formula work that the probability of A given E, so A given E, is the probability of A and E, and it's always over the given. So in this case, the given was E. So that guy always mixed up the denominator. So we already have the info for this. We just have to plug it into the formula. So we already know that A and E was 15%. And we were already told in the original given information that E is 58%. So simply 15 out of 58, which would be acceptable, or if you wanted to, put that into a calculator and come up with a decimal for that, that would be okay too. So hence or otherwise, so now moving on from there. So hence meaning now use that information or with some other method, show that A and E are not independent events. So remember what it would take for events to be independent. If A and E are independent, that means A and E is equal to, let me just write it out. This is one of our formulas that's in our formula packet. But if events are independent, then this statement would have to be true. The A and E equals A times E. So that would have to be true. This equation would have to be true if the events are independent. But if I plug in the information that we know that A and E was 0.15. We know that A was 29. And we know that E was 58. So obviously this times this does not equal this. So we are showing by the use of that formula that that information does not check out, so therefore they are not independent events. The other way you could have justified that would be to say that when you have a given formula, so here's kind of the hence part. I started out with the otherwise part. I used a different method, but the hence part, if I use this information, in a given scenario, if events are independent, then A given E would equal the probability of A. So there's kind of a shortcut to that. So because if they're independent, the E's cancel, and all you're left with is A. But we're seeing right here that A given E does not equal A. Right? This is not the probability of A, therefore the events are not independent. All right, moving on. So part C, given a lot of information in here. So this one's a little bit ugly. We got a lot going on here, but we'll just use some formulas here to make it work for us. So now they're kind of giving us just a new scenario. So it's a different place. Now we're at University of Foxchester. So similar case, but some differences as well. So they're still saying that the neither case is still 28%. This is still true. However, we got A is, first of all, independent of E, and we also know that engineering is 2 times more popular than A. So a couple things we're going to use here. They want us to come up with an expression for A and E in terms of just A. And so if we kind of use the information here, we're just going to start plugging in what we know. The fact that they're independent is really important. They even put that in bold for us to make sure we didn't miss that thought. So let's start using a little formula work here for what we know. One big formula that we work with quite a bit was the one we started off with. So let me just write that down. So the probability of A or E is equal to the probability of A plus E minus A and E. So we're going to start plugging in some info right here. So they're giving us this formula right here. Just for a little sake of substitution, if I were to subtract this over to the other side, then I know that A or E is equal to 1 minus N. So I'm going to sub that in for this one right here. So 1 minus the probability of N, which is neither. So we're subbing that in for A or E. And then we got our probability of A. We do a little more substitution on this side as well. So we got the probability of A. Now they told us up above that engineering is 2 times more popular than A. So in other words, in math symbols, E is 2 times A. And so just using that idea, I can make a little substitution for him. So instead of E, I'm allowed to put 2 times the probability of A. And then minus probability of A and E. Right. So in this one, they said they wanted the expression for A and E. So ultimately, that means I want to get him by himself. So I'll get everything else onto the other side. And based on what they told us up above, we also know that probability of neither is 28%. So I can sub in my 28 right there. So 1 minus 28% we know is 72. And now I got my probability of A plus 2 probability of A minus this guy. Okay, so I want to get him by himself because he's got the negative in front of him. I am going to choose to move this guy over to the left so I can add him over and get rid of that negative sign. At the same time, I'm going to subtract him over to the right, so I'm going to do a few things in one step here. So probability of A and E is going over to the left. A plus 2A is 3A. And I'm going to subtract that 0.72 over to this side. And there we go. We have our expression for A and E solely in terms of A. There's no E on this side. So we took care of that. So last part of the question here, hence or otherwise, meaning hence you can use this information, or if you have some other way to do it, then find the probability that architecture is chosen at the University of Wrksht. In other words, solve for the probability of A. So let me move this up a little bit so I have room to write. So I'm going to work with, obviously, this equation. They did say hence or otherwise. The hence is your hint to tell you to use what you just did. So because these events are independent now, they've made that real clear. They bolded the word independent. So remember what that means. In independent events, A and E is equal to A times E. And so I'm going to replace this left side with A times E. So I have the probability of A times the probability of E, but remember that E was 2 times A. So instead of putting an E here, I want to put 2 times the probability of A. Just bring the other stuff down for now. Okay, so if I multiply these two together, A times A is A squared. So I have 2 times the probability of A squared. So in this sense, even though it's like P of A, I'm gonna drop the P and just put the letter A just so it looks a little more obvious as to what we're doing on this. So let me just call it 2A squared. 3A minus 0.72. So now you would recognize maybe this as a quadratic equation. And so you would solve this like any other quadratic. We would say get everything onto one side so that it equals 0. And then I could just use any method for solving a quadratic. This guy's a little ugly because of the decimal, so that would make factoring much harder. So you'd probably just want to use the quadratic formula. You could use a graphing method in the calculator for solving quadratics. That works too. Whatever is best to you at this point. So you are going to come out with 2 solutions. Notice that one of those solutions is too big. It would be impossible. So the two solutions you get are either 0.3 or 1.3, but 1.3 doesn't make sense. It can't be bigger than 1. We're dealing with probabilities. You can't have more than 100% or a number bigger than 1 in terms of decimals. So 1.3 would have to be out, and we would have to use the other, which is 0.3. All right, moving on to number 4. All right, here we go. So 6-sided die has 4 green faces and 2 yellow faces. Just note that to myself, 4 green, 2 yellow. For a roll of the die, let G represent the event that what is showing on top is green, and Y is going to represent the event that it's showing a yellow. So I'm tossing a die. Obviously 4 out of the 6 are green, 2 out of the 6 are yellow. So those are like our probabilities for those. Alright, so we got Tiago plays a game which involves either 1 or 2 rolls of the dice. If the uppermost face is green, he gets 4 points and the game is over. But if he tosses a yellow on the first toss, then he gets 2 points and he gets to roll 1 more time. So the outcomes are represented in the tree diagram below. So again, here's like the first roll of the dice. So notice if he rolls a green, the game is over. And he gets 4 points, but the game is over. But if he rolls a yellow, then he gets 2 points, and then he gets 1 more toss, and obviously on the next toss it could either be green or yellow. So kind of a good tree diagram right there to show the possible scenarios. So let's see what they want for us. So find the values of H, I, J, and K. So here is the first toss of the dice. We already found out for H that if you were to toss the dice for the green one, right, there's 4 out of 6 ways for him to get a green on the first toss. So we know this H represents those 4, 6. And the yellows, right, they're 2 out of the 6 were yellow. And then he gets to toss it again. If you were to toss the die again, the probability of it coming up green is still 4, 6. And the probability of it coming up yellow is still 2, 6. And if you want to reduce those, you can. Obviously, those could be 2/3 and 1/3 if you want to do it that way. So now we're talking about the points scored in the game. So X is going to represent the points, total points in the game. So what's the probability that the total points in the game is 4? So he could have gotten 4 points with this scenario right here for 4, 6. So this was one option right here. This would have given him 4 points. Let's just look at the other 2 possible outcomes for a minute. If he rolled a yellow and got 2 points, and then rolled again and got green, that's another 4 points. That would have given him 6 points. And so that's not one of our winners. However, if he tossed a yellow and got 2 points, tossed another yellow and got another 2 points, this would have been a winning scenario because that would have added up to 4. So we're basically looking at these 2 cases right here. In this case, it was only one toss of the die, so it's a 4, 6 possibility. Let me just do my work up here. So there's one way he could have done it, or, so I'm going to add, or he could have gone with this case right here, right? But what would have led to those 4 points? He would have had to do yellow and yellow, which is 2, 6 times 2, 6. Let me just write all that out. Which would have been that case right there. So these are the possible outcomes. So either he got a green on the first roll, or he got yellow and yellow. And that would have been the other scenario. Let me just reduce those so I get smaller numbers to work with. So or, and then this would have been 1/3 times 1/3, which is 1/9. So I guess I need common denominators, so 2/3 could become 6/9. So 6/9 plus 1/9 is 7/9. So that would have been our answer for the 2 possible cases that could have given him 4 points. What's the probability that he earned 6 points? Well, there was only one 6-point case, and it's this one right here. So he would have had to toss a yellow, then a green, in order for that to happen. So it's 2, 6 times 4, 6, or you could have said 1/3 times 2/3, and that would give it to you as well. Alright, so in a table show the probability distribution of X. So in this case, remember, X represented total number of points, and there are only 2 possible outcomes, as we saw right here on the tree diagram. It could only either be 4 points or 6 points, so this would be a pretty small distribution table. So we know that X could either be 4 or 6. Sorry, it's a simple table, but anyway, so the probability of all that, we saw that the probability that X could equal 4 was 7/9, and the probability that total value of 6 points was 2/9. So there's our distribution table. So the expected value, if we do 4 times 7/9 plus 6 times 2/9 is going to get you that expected value. So you just multiply that out, and that will do that for you. So moving on here to the very last part. So if the total score is 6, he wins $16. Otherwise, he wins nothing. So he plays the game 3 times. Find the probability that he wins $32. So there is two ways you could do this. I'll kind of show you both here real quick. But if the total score is 6, right? So we saw right here that's a 2/9 possibility, and he wins $16. So if he's going to win $32, obviously this has to happen twice, and he's going to play the game 3 times. So this means he's going to win twice. So this would happen twice, and then on the other roll it would not happen. So one way we could look at that is with one of the formulas that's in our binomial theorem expansion that we've looked at before, and that's with the combination. So that's the one that kind of looks like this. So it's like NCR and then a to the n minus r, b to the r. So we could look at it with a case like this. As far as the n, the number of trials we know is a 3. A is our probability of success, and B is our probability of failure. So success is him getting a 6, which we know is 2/9. So our probability of success is 2/9. And our failure is if he does not get a 6, which the only other option then was the 7/9. So that's the probability of not getting a 6, or probability of failure. So as we said a second ago, in order for him to get this amount twice and get that $32 means he's got to have success twice and failure once. And so it would look something like this. So this R is always the same as this R. So if it's a 1, then I would put a 1 right there. So we could punch it in that way with the 3C1. Let me do that real quick. So we got 3C1 times 2/9 to the second times 7/9 to the first. And so there's one way to get that answer. So we have about 11.5% chance of that happening. So that's one option. The other way you could have done that is because it comes with a specific number of trials, right? He's doing this 3 times. And this is a case where it doesn't say at least or at most. It is a specific number of cases where he must win exactly twice. We can use the binomial PDF feature. So if I go under distribution and go to binomial PDF, right, then there's going to be 3 trials. The probability of success is 2/9, and we need this to happen twice, right, for him to win that exact amount of money. So if I put those in, so there we go, same answer, about 11.5%. So either way we could do that.